This is applying the correct amount of pesticides. So welcome everyone. I appreciate you guys joining us here tonight. This is a pretty cool class. I like teaching it. I love teaching calibration. I love teaching anything to do with pesticides. And so to be honest with you guys, let's go ahead and get started by asking the question, why do we have pesticide failures? What is the number one reason? What is the number one reason we will have a pesticide failure?
Don't read directions.
True. Yeah. I would never read directions. We're all
misidentifying the pest.
That is the number one reason. Exactly. Misidentification of the pest. We don't know what it is that we're targeting. And so that's why we will have a pesticide failure.
Huh.
And so Mr. and Ms. Smith are going to call us back out to the property, and we're going to have to make another application once we correctly identify the problem or the problem pest. And so when it comes to this, to use the pesticide successfully, we must apply the correct amount of pesticide over the target area in a uniform way. Errors in rate or uniformity may waste money, injure plants, damage the environment, fail to control the pest, and result in fines for illegal application. In every situation, you should know rather than guess whether you are applying the correct amount of pesticide. Now, back to that subject right there of incorrectly identifying the pest. So what do you think the second most popular reason we have a pesticide failure is?
The amount of chemicals?
Yes. Yeah, exactly what we're talking about tonight. Applying the incorrect amount would be the second reason why we have pesticide failures. And so when it comes to applying the correct amount, do you think we're going to be in a little more trouble if we apply too little of a pesticide or too much of a pesticide? When I say trouble, do you think it's going to hurt the pocketbook and the wallet more so with less application or applying more than we need?
More as far as money.
More.
Yeah. But sit back there and look at that. If we apply more than needed, we've wasted money, yes. But do you think we've killed the pest? Do you think we've done our job?
No.
Why is that?
Well, you've got to have enough chemicals to do the job.
Well, yeah, but if we're applying too much of the chemical, do you think we've killed the target pest?
More than likely.
More than likely, yes. Yeah, we've killed it. What happens when we don't use enough pesticide? We're not going to kill it. So what do you think we're going to have to do again because we didn't kill the target pest?
Reapply.
Reapply. What does that cost?
It's going to be more money.
More money. So yes, we're having to go back twice and we're having to spray it again. And we're probably a little bit mad at ourselves. So we're probably going to mix it a little high the second time, right?
Right. Yes.
We're probably spending more money if we apply less pesticides. So we're having to go back. So little food for thought when it comes to that. And so when we are applying our pesticides, we got to measure our treatment area. Usually the smaller sites are measured in square feet. Larger sites are measured in acres. We've got to convert all of that either from, gallons per acres down to, square feet. Our mistakes can be costly. And then we always need to treat or subtract the areas that not treated, because a lot of these software programs out there that we use, Google Earth, and I mean, there's numerous ones that we can measure these properties, even, Forsyth County geodata here in Forsyth County, pretty good at getting close to our property measurements. A lot of the times we forget to subtract out those driveways, those shrub beds, and even our sidewalks. Here we have our basic shapes, and this is a golf course hole. I love this problem because it does, show you how to break it down. We've got some yards that are cut up all over the place. You can't just go out and measure, length times width to get the square footage of these yards. You got to break it down into geometric shapes that we can figure pretty easily. And so with the circle, we know that it's pi r squared, 3.14 times radius squared. Pi is 3.14. It's the constant. And that's how we're going to find the area of the circle. And so here, the T box we've got for our circle, we got a radius of 70 feet. And so we're saying pi, or 3.14 times 70, the radius square, we've got a T box of around 15,386 square feet. The fairway, we've got a rectangle, which is length times width. And so we've got 170 feet. It's roughly 90 feet wide. So we got an average of about 15,300 square feet for that fairway. And then we got a little triangle out there up front. And the area of a triangle is base times height divided by 2. So we'll multiply the base by the height and then divide by 2. And we have 90 feet times the 50 divided by 2 is going to give us, 2250 square feet. And then we've got our hole there. And it is a trapezoid. And we're going to multiply the average length of the parallel sides, A and B, and then by the height. So 115 feet there on the front side. And then we got 140. We're adding those two together. And then we're going to divide by 2 and multiply it times the 40. And so we got 5,100 square feet for, a golf course hole, 5,000 square feet shy of an acre, 38,036 square feet. So we got to get out there and measure it. And there's all kinds of tools out there that can help us do that if we're in the field. Measuring wheels, and they've got the measuring wheels now that connect to your phones, and I'll actually draw it out for you. So it's getting a lot easier than it used to be. But calibration, when do we need to calibrate?
Before every application.
Before every application. That's right. That's right. Now's the time of year we're getting our equipment out. We're cleaning it. We're getting it prepped for the season. We're getting excited. I know we were out in the field today, and I'm still cold, but I'm ready for some warm weather. But we're getting our stuff ready. We're getting our tractors ready, getting our mowers ready, getting those push spreaders ready. But we have to calibrate this equipment every time we use it. Now, can anybody tell me any other time we might want to calibrate?
After lunch.
After every use.
Yeah, exactly. Why's that, Mr. Melvin?
Getting kind of tired and lazy.
We are. We get our bellies full. We slow down. We get sluggish. It's getting the hotter part of the day, and we're slowing down. So we might have been walking, 2 miles an hour this morning. Well, this afternoon, we might be down to 1 mile an hour walking. And that is going to do what to our application rate when we slow down? If we calibrated it at normal walking speed this morning and we've cut our travel speed in half, what is that doing to the application rate?
You're applying
Putting more down.
Increases it.
Yeah. Yeah. And if we were at 2 miles per hour that morning, that's humping it. But if we slow down to 1, we're actually doubling the application rate there. So we're wasting money, and we don't want to do that. And we don't want to put out more product than needed because we're not protecting the environment. The calibration is a process of measuring output and adjusting your equipment to apply the right amount of pesticide to the target area. It is completed by the individual making application. So it has to be your technicians. You can't calibrate the equipment for them in the mornings. You've got to let them do it. You need to give them the time. They've got to have the space to do it. Trust me, it's going to save you money, but they need to do it every single morning before they leave out. And then, like I said, possibly at lunch. But then what do they need to do to that calibrated equipment in the evenings when they get home?
Clean it.
Clean it. Get it ready for the next morning. And your properly calibrated equipment will deliver the right amount of pesticide and apply it uniformly. The label will tell us the application rate. We're going to look for things such as 4 ounces per 1,000 square feet. I love breaking down our properties to the 1,000 square feet blocks It's just a whole lot easier. I can calculate exactly the chemical based on breaking it down. If we got 23,000 square feet on a site, I'm like, we got 23 1,000 square foot blocks. You may see it in 3 ounces per gallon. That's product per volume. And then you may see a 2% solution with percent solution mixed with water. Well, you got to find that on the label. And we need to read these labels every time we go out. We need to keep them in the vehicles. We need to keep them in the office. If you're applying that pesticide and you know you're going to be spraying it this week, or you're going to be spraying it, for the next little bit, go ahead and start reading those pesticide labels. It may have been a year since you've used that pesticide again. So touch up on it every time you use it. But when to calibrate, we've talked about that before using it the first time each year. When changing the type of pesticide that we may be using, when changing the rate and speed which is applied, that's your lunch right there. That is your lunch right there when you're slowing down. And then when equipment is moved from one site to another, it's especially important with rotary spreaders because their settings are easily knocked out of place. Those things get tore up in the back of a pickup truck. You got to have a way to actually get them secured in the back of the truck. Now, it looks like somebody's got their hand up in the chat box. I'm not able.
Yeah, that's me, Major.
Oh, hey, Major.
I just got my dad on, Mike Collier.
Oh, okay. All right. What is his number?
676.
026
6976.
6976. But the prefix is 026, right? All right. So 026 6976.
Gotcha.
Thank you, sir.
Hey, man, this
Hey.
is Charles Robertson. I just got in too. It wouldn't
Hey,
let me in.
Charles.
Am I good, or I need to come back another day? Or
No. Let's see. What's your license number?
oh shoot, I don't have a clue.
I'll give it to me at the end.
Okay. All right.
All right. But with this calibration, we do got to take the time and do it every single day. A lot of people don't want to pay their employees to do that in the morning. They feel like they're wasting time, but trust me, you will save money in the long run. All right. So with our calibration, make sure you're choosing the right equipment that you want to use. Our walking speed is usually 2 to 3 miles per hour. Like I said, we may start out 2.5, and each employee is going to be different, each technician. So you may have someone that's a little bit taller. They may be, scooting across the turf pretty quick at 3 miles an hour. And then you may have someone that is at 2 miles an hour. And so in the evening hours, you are going to slow down. But when you think these guys pick up the pace really, really fast, if they're looking at their route sheet and they don't necessarily think they're going to get it all done, what do they start doing around 4 o'clock?
Cutting corners.
Yeah, cutting corners. But they're like, if I don't get back to the shop, they're speeding up. They're speeding up. Exactly. And so they've calibrated the equipment earlier in the day at a slower speed. When they're actually walking faster, when it's getting closer to quitting time, what are they doing with the application rate?
They're not putting out as much.
Not putting out enough. Exactly. Good job. And that is going to make you have service calls. Mr. and Ms. Smith's going to call you back and say, you didn't kill those weeds in my backyard. We paid for it. You're going to have to come back and do it again. All right. So using backpacks. A lot of people don't like it. I still love the backpack. I love pushing out my fertility using a granular spreader, and I like spraying weeds with a backpack. Now, if we have a large property that's full of weeds, we'll pull a hose off a truck. But the backpack gets the job done for us, and I like it. You'll have compressed air up to 30 PSI. The pressure drops as the solution is sprayed, unless you've got one of those battery-operated ones that'll keep it constant for you. Those things are cool. And if you have the gauge, try to keep the pressure within 10 PSI of the initial pressure. When calibrating by area, if you're spraying the pesticide to an area measured in square feet, calibrate the sprayer by staking out 1,000 square foot test plot. Example, 20 by 50 on a surface similar to the treatment area or similar to the treatment site. So, and basically that's saying if it's a flat ground, you want flat ground. If you're going somewhere that's a rolly, hilly, you may want to find a place at the shop that's got some hills and stuff too, because that's going to change your technician's speed as well. But somewhere that you can see the water, so either on asphalt, gravel, parking lot, whatever, just have it marked out. The easiest thing to do is put some stakes out there in your parking lot so these guys can do it first thing in the morning and they can mark it out and get it done. Step 1, fill the sprayer tank half full with water, no pesticide, maintain the pumping pressure that you'll use during the application, and then record the number of seconds it takes to spray the test plot evenly while walking at a comfortable, steady pace. It's a good idea to spray the test plot 2 or 3 times and then figure the average time that you're getting from this and use that average time in your calibration. Step 2, stand still and spray into a container the average time found in step 1. The number of ounces collected equals the amount of spray delivered to 1,000 square feet. This number, you can calculate the amount of pesticide and water needed to treat the target area. And we have a sample problem here. We've read our labels. We know we're getting ready to spray some herbicides to a lawn that's 40 feet by 65 feet. And we've read the label. It says our application rate is 2 ounces of herbicide to be mixed with a sufficient amount of water to treat 1,000 square feet. This can be expressed as 2 ounces per 1,000. The area to be treated is 2,600 feet, the 40 by 65. Test plot to cover 1,000 square feet is 80 seconds. The amount of water that we collect in 80 seconds is 57 ounces. So our sprayer output is 57 ounces per 1,000 square feet. So determine the total spray mixture. That's different than our actual pesticide volume. Our total spray mixture, we would multiply the target area by the sprayer output. So 2,600 square feet times the 57 ounces per 1,000 square feet is going to give us 148.2 ounces. We'll round down anytime we're talking about pesticides to 148. And that's the 148,200 ounces divided by 1,000. And so next, to solve this problem, we're going to multiply it. Well, let's repeat what we just did. So second step, to determine the amount of herbicide needed, multiply the target area by the labeled application rate. This is the amount of pesticide. Our label says 2 ounces per 1,000. So we have 2,600 times 2 ounces per 1,000. It's going to give us 5,200 divided by 1,000. So we need 5.2 ounces of our herbicide. And so to treat that target area, a little more than 5 ounces of herbicide should be added to 143 ounces of water. 148 minus 5. Why, in this problem right here, it says we need total spray mixture of 148. Why are we subtracting the 5 ounces from it?
To get the correct total volume.
To get the correct total volume, yes. Our total volume is 148. And we're actually going to put in roughly, 5 ounces of herbicide. So we say the 148 minus the 5, because we've got to add that 5 ounces to 142, which gives us that total spray of 148. And since there's 128 ounces in a gallon, this will mean adding 5 ounces of herbicide to 1.1 gallon of water, which is our 143 divided by 128. So easy enough. I love the backpack sprayer, and that is the easiest way to get your technicians, started when you're hiring them. So calibrating by volume, this is like when we're going to spray it to wet it. It's almost like painting the plants or painting the turf grass. Mainly we'd do this with probably ornamentals. We're going to add water, no pesticide to the tank, pressurize it, then record the number of seconds to spray a representative plant thoroughly. So we're going to find the plants, however many we got, find one that's like, very average to all of them. And we're going to wet that plant very thoroughly. Then we're going to spray into a container for the length of time that it took us to wet this plant. And we'll use the number that we calculate. We'll use this number to calculate the amount of water and product needed. So we're going to spray a plant, record the time, and then we're going to spray it into a container, and then make sure that we're holding the trigger down for the same amount of time of the plant and the container. And so here's a good problem: spraying some azaleas. We've read the pesticide label, and it's saying that we need 3 ounces of insecticide per gallon. Number of plants to treat, we've got 18. The seconds to spray one average plant was 12. So the amount of water collected in 12 seconds is 10 ounces. So next, we're going to figure out how much total spray volume we're going to need. We're going to multiply the total number of plants to treat by the amount of water collected in one plant. So that is the 18 times the 10 ounces. And we're converting our ounces to gallons. 180 divided by 128, which is 1.4 gallons. So determine the amount of insecticide we need, multiply the labeled rate by the total spray mixture. And it says we needed 3 ounces per gallon. And we have 1.4 gallons of the total. So we need 4.2 ounces. Add a little more of 4 ounces of insecticide to 176 ounces of water. Again, we've got to subtract out the 4 ounces of insecticide from the total spray mixture to get the total spray mixture of 180. And that's going to get us our 18 azaleas. And so that is a good backpack problem. We wouldn't want to pull, a hose off a truck for that. Spot treatments and percent solutions. Calibration is usually not necessary in spot treatments. The label will state like 6 tablespoons per 1 gallon of water to be sprayed wet. Or, if we're spot spraying, weeds and shrub beds or something like that, it's a lot easier. So mix 3 gallons of a 2% pesticide solution in water. We're going to convert the 2% to a decimal. So we got 2 divided by 100 is 0.02. And then to determine the number of ounces of pesticide needed per gallon, we'll multiply the rate per gallon, 0.02 by 100 by 128, because there's 128 ounces in a gallon. So 0.02 times 128, we need 2.6 ounces. To determine the amount of pesticide needed, multiply the amount of pesticide per gallon by total spray mixture, 2.6 times 3 gallons, 7.8. Mix a little less than 8 ounces of pesticide with slightly less than 3 gallons of water. Nozzle knowledge. Just some good diagrams from it. It comes directly from the apply and correct the APC manual that they used to have at the Department of Ag. But you got your nozzle body, the diaphragm, strainer, tip, cap, nozzle parts. Anybody spraying? Anybody seeing weeds pop up in turf grass now? Is everybody kind of chilling out for a few weeks before we get started? Y'all getting quiet.
Got a mixture of all kind of weeds on fence lines.
On
It's
fence
been
lines?
raining too much.
It has been raining, ain't it? Oh my gosh. Dang. But then we got our nozzle types: hollow cone, standard flat, a solid cone. But then to spray uniformly with the flat fan nozzles, we'll adjust so that 30 to 50% of the spray pattern overlaps each other. Spray guns. Now, this is pulling the hose off the truck. Not my favorite thing to do. I love having this a part of our company, but I don't want to be the one out there doing this. That is the loneliest job in the world, to be honest with you. But to calibrate this, we're going to divide 1,000 square feet by your swath width to determine the distance of the test course. We're going to spray that test course with water using the technique you will use for your application. Begin spraying just before you enter the course. You want to make sure you get that front line as well. Record the number of seconds to spray the test course. Average it 3 times. spray in a bucket the number of seconds from step 3, then measure and convert to gallons. The amount collected is your spray gun output per 1,000 square feet. And for acres, you'd multiply by 43.56 since there is 43,560 square feet in an acre. And your problem here, the calibration of the spray gun, for a swath width of 5 feet, you're going to mark a test course that is 200 feet long. The 5 times 200 is the 1,000 square feet. Average the time in seconds to spray the 200-foot test course. We've done it once at 77 seconds, once at 79, and the last time at 78. And so we've got an average of 78 seconds. Gallon sprayed into the bucket in 78 seconds is 5.25. The output is 5.25 gallons per 1,000 square feet, or 228 gallons per acre. 5.25 times the 43.56. So note, if your calibration output is not within 5% of the label rate, you've got to adjust your walking speed or your nozzle or even your pressure. Recalibrate until your output comes within 5% of the label rate. We got some good problems to see with that. With your boom sprayer, hydraulic sprayers produce pressures up to 500 square PSI. The application rates can vary widely. Some materials are applied at a rate of 1 quart per 1,000 square feet, and others may be applied at 100 gallons or more per acre. The height of the nozzle above the ground determines the swath width or the effective spray area per nozzle. The height is usually 14 to 18 inches above the target surface. So you got to watch that and make sure that it's lowered, especially if you're using like a boom sprayer on the back of a lawn tractor or whatever. That things can move up and down. Again, nozzle spacing, you want the overlap. Pressure must increase 4 times to double your sprayer output. Adjust pressure only to make small changes in the output. Again, when you're doubling your speed, you're cutting your application rate in half. And when you're dropping that speed, you're doubling it. So pre-calibration, check your sprayer pattern. Check all components, clean them. Make sure you've got the correct type needed for the application. Clean them and the screens with soapy water and a soft brush. Rinse the spray tank and partially fill with clean water. Pressurize the sprayer and then flush your hoses and your boom. Reattach your nozzle tips and then spray water on the paved surface. Here's an overhead view of it. They're getting 50% overlap. Here we can see some streaks in the pattern. This is showing either problems with the nozzle height, the alignment, or the output. We got some that are getting, way too much. And then some that are very, not getting any hardly. So with the container in ounces, catch the output from each nozzle for 20 seconds. You're going to mount it underneath it, or lower it or however you're going to do it, but you got to collect it. Add the amounts and divide by the number of nozzles for an average output. If the output is 10% above or below the average, replace that nozzle. Repeat step 1 and use the results for average in steps 2 and 3. And we got a little chart here that's going to help with that. So we've got a boom sprayer that's got 8 nozzles. You can see nozzle 1, 2, 3, 4, 5, 6, 7, 8. We're catching them in a container. Well, first nozzle, we've got 16 ounces. Second one, 12. The third one is 15. 4 is 16. 5 is 16. 6 is 15. 7, 14. And 8 is 19. So the lowest one looks like is 12. And the highest one is 19. We're going to add all these up. And that is basically 123 divided by 8. So we got an average of 15.4. Our acceptable range is 13.9 to 16.9. The 15.4 plus or minus that 10%. So 10% of 15.4 is your 13.9. And if you added it to it, you've got the 16.9. So with number 2 and number 8, we're going to have to replace them simply because they're not in that acceptable range of 13.9 to 16.2. So we're going to replace them. And then we're going to go and do another output test. Same nozzles, changed out 2 and 8. And look how much more uniform this is. We got 15, 16, 15, 16, 16, 15, 15, 17. Our average is 15.6. 125 divided by 8. So 10% of the 15.6 subtracted from it is going to be 14. Added to it is going to be 17.2. So output from all nozzles is now within the acceptable range. There's nothing below 14, and there's nothing above 17.2. So we're good to go with this boom sprayer. So we're going to mark that 200-foot course on a site that is typical of the surface and the soil conditions of the area to be sprayed. Fill the tank half full. Test which gear and RPM will allow the sprayer to maintain pressure on the nozzles between a constant of 3 to 5 miles per hour. Drive the sprayer on the 200-foot course 3 times. Start far enough away to reach the speed before the first marker. We want to make sure that we're getting that line wet as we cross over it. So measuring the ground speed, our course length is 200 feet. The test runs in times was 31.5, 30.3, and 29.2. Our average, add them up, divide by 3, we've got 30.3. So our miles per hour is the 200 feet times the 60 divided by the 30.3 seconds times 88. We're going to run 4.5 miles per hour. So then we're going to collect for 1 minute or 30 seconds times 2, divide the number of ounces per minute, OPM by 128 to find the gallons per minute. Measure our distance in inches between the tips of the adjacent nozzles. This is our nozzle swath width. Determine the sprayer output in gallons per acre by inserting the values from steps 2 and 3 and then the miles per hour from your test course in the following formula. And there is that gallons per acre. We've got our gallons per minute times a constant of 5940 divided by our miles per hour times the W, which is our swath width. Oh, so we're going to mix pesticide with water to treat 2.5 acres using a boom sprayer. We already know the label rate. We've read our label. We're going to put out 5 pints per acre in spray volume of 30 gallons per acre. We just did our miles per hour formulation in the previous problem right here. And so we know that's 4.5. We know our nozzle spacing is 20 inches. Our average nozzle output was 56 ounces per minute or 0.44 gallons per minute. We did that calculation previously and then determine our sprayer output in gallons per acre, 0.44 times a constant of 5940 divided by 4.5 times 20. And so we have 29. This output was in 5% of the gallons per acre. We got 30 plus or minus the 150, so no adjustment is needed. We're good to go. So determine our total spray mixture needed. Multiply the target area by the sprayer output, 2.5 acres times 29 gallons per acre for 72.5 gallons. To determine the amount of pesticide needed, we're going to multiply the target area by the label rate, 2.5 acres times 5 pints per acre. So we need 12.5 pints. So to treat the 2.5 acres, add 12.5 pints of pesticide to 70.9. We're going to subtract out the 12.5 pints from the 72.5 gallons to get that 70.9 gallons of water and our pesticide.
Eric,
Yes, sir.
is there a place where you can go and find all these charts?
Yeah. I can email you this formula, but these exactly right here, what we're looking at, that came out of your ornamental and turf book.
Okay.
These are problems directly from that.
Okay.
Because it's got the blue. It's in the blue.
The big book that the state published.
Yeah.
The pesticide book.
Yeah, the O&T book, the ornamental and turf.
Right. Okay.
All right. So if your sprayer's output is not within 5% of the gallons per acre on the label recommendation, then we got to adjust our pressure, our speed, or our nozzles according to the guidelines in table point 10.2. And so if measured output is within 5 to 10%, we need to increase the pressure to deliver more spray or decrease the pressure to deliver less spray. If measured output varies from label gallons per acre by 10 to 25%, adjust your travel speed. Slower speed will deliver more spray, and then the faster will deliver less. Measure your speed under field conditions and use new speed in figuring the GPA. And then if measured output varies from label rate more than 25%, you need to change the nozzles and repeat the pre-calibration check and calibration process. Very seldom do we use boom sprayers. I mean, we do in the strawberry farm, but we're not using booms that much in residential lawns. I do like the little ride-on stand, the stand-up sprayer spreaders. Those things look pretty cool. We had one back in the day, but it's no longer in commission. But it had, I think it had 3 spray nozzles out front. Granular spreaders, easy to calibrate. You do need a hard top. It would be easy to do that. It makes it a lot easier to clean up. But you need to get some jars or you need to get some pans. But to calibrate this, we're going to establish our swath width, determine the application rate, and then determine whether or not we're going to use a drop or rotary spreader. Not too many people use drop spreaders anymore. It's primarily rotary spreaders, just because we can cover a lot more speed. So I'm just going to kind of skip over that drop spreader. But calibrating these rotary spreaders, which these things are going to be hot to trot here in a couple weeks when we start putting out those first rounds of pre-emergent. But we need to get some boxes. We need to put one box in the middle and then space the remaining on either side of it at 2-foot centers. We're going to make 3 passes over the boxes. So basically we're going to push our spreader to the boxes with the actual fertilizer or pesticide in the hopper. This is the only time that we're actually using the pesticide for calibration purposes. We're going to go over it once. We're going to come back around. We're going to go over it again. Then we're going to go over it a third time. We're going to make these 3 passes. We're going to record the weight, or we're going to pour it into jars marked with the box number. I like pouring it into the jars. The center jar should have the most product with the mounts tapering off. So you're going to see it kind of taper off. Find the jars on both sides that have half the product of the middle jar, and distance is your swath width. So if you got that jar in the middle, let's say it's got 8 ounces, you want to find or 5, whatever you're measuring it to 8. You want to get down to where it's at 4 on these jars here. And the distance in between those 2 with 4 in it is going to be your swath width. And not a bad picture, but this guy, he's making the passes over it. He's got them in the boxes. He's going to go over it 3 times, but this next slide is actually a little bit better to see it. You're pushing that spreader. And here we've got 9 jars total. And so we've got 5 is one in the middle. So there's 4 on either side. We make 3 passes over it. And jar number 2 and jar number 8 is actually got half of what is in jar number 5. And so the distance between these, because they're 2 foot apart. So 2, 4, 6, 8, 10, 12. We've got a swath width of 12 foot. And so step 1, we could weigh out enough product to load the spreader for a calibration test over the distance that can easily be converted to 1,000 square feet. 2, we're going to select our testing setting to deliver 1/2 the labeled rate. Note, spreader settings are not linear, so using a number half the number recommended on the product label will not result in half the application rate. You'll need to experiment with your equipment and then apply the material over the measured distance and then weigh the product remaining in the spreader. The difference in pounds should be within 10% of 1/2 of the pesticide label rate. Adjust the size of the gate opening to your application rate is in range. And so we're going to look at a problem, but here is table 10.3. This is right out of our books. If we've got our feet, our test course is going to tell us how long it needs to be. Well, we just measured right here that we got a 12-foot width. And so we need to have a test course length of 84 feet. So calibrate this rotary spreader to apply a turf herbicide using 2 passes over the treatment site. Our label rate is 80 pounds per acre, and our effective swath width is 12 feet. So the length of our calibration course needs to be 84 based on this chart right here. The beginning weight of the product is 908 grams or 2 pounds. The end weight of the product is 426 grams. The difference is 482 grams or 1.06 pounds. The 482 divided by 454, 1 pound. The spreader is calibrated to apply 1.06 pounds per 1,000 square feet. Our rate per acre is rate per 1,000 square feet times 43.56, or 1.06 times 43.56 equals 46.2 pounds per acre. This rate is higher than the rate needed of 40 pounds per acre, 1/2 of 80 pounds per acre. So adjust the spreader by reducing the gate opening until the rate falls within 10% of 40 pounds, which is between 36 and 44. And so we were just a little bit too high there. We're actually 2.2 pounds, a little bit higher than needed. And so to determine the amount of granular insecticide needed to treat the 2.5 acres, label rate 3 pounds per 1,000 square feet, convert the acres to square feet. We got 108,900 square feet, 2.5 times the 43,560. And so to get the total number of product needed, multiply the area by the application rate. 108,900 square feet times 3 pounds per 1,000. We've got 326,700 pounds divided by 1,000. We need 326.7 pounds to do the 2.5 acres. So roughly, over 6 bags. And if we want to spray it, do it like this, if we want to go over it twice, we can use the right angle method, make 2 passes at 90 degrees. So starting, coming here, and then going back this way. Not my favorite way to do it. I'd much rather do the half width method. Doing the parallel passes, 1/2 the effective swath width. So instead of 12 feet, I'm at 6 feet if I'm having to double it. So that concludes the actual slideshow. Has anybody got any questions, comments, concerns?